નવા જ વિષયની વાત કરવાની છે. વિષયનું ટાઇટલ આ પ્રમાણે છે, માઇક્રો ટુ મેક્રો. આપણે બીજી બધી ઘણી વાતો કરતા હોઈએ છીએ. ગ્રહો વિશે વાત કરીએ, ગેલેક્સી વિશે વાત કરીએ. આ એક નવો વિષય એટલા માટે છે કે આ બધી માહિતી, આ દૂર દૂરની ઘણા બધા પ્રકાશ વર્ષ દૂર હોય એવા પદાર્થોની માહિતી આપણા સુધી કેવી રીતે પહોંચે છે, એક મોટો સવાલ છે. સામાન્ય રીતે તો આપણે કહીએ કે પ્રકાશ મારફતે, એટલે કે ફોટો. પણ માત્ર ફોટો નહીં, એની પણ અમુક મર્યાદા થાય. પણ એના કરતાં પણ અતિશય સૂક્ષ્મ કહી શકાય એવા કણો પણ અસ્તિત્વ ધરાવે છે. પાર્ટિકલ ફિઝિક્સ જે હોય છે એના ઉપર કામ કરતા હોય છે. આ હિગ્સ બોઝોનની શોધ જ્યારે થઈ ત્યારે એમાં થોડો ઇન્ટરેસ્ટ લોકોને વધ્યો હતો. પણ એને અને એસ્ટ્રોનોમી, એસ્ટ્રોફિઝિક્સને કંઈ સંબંધ ખરો કે નહીં? એટલે સામાન્ય રીતે આ વિષય ચર્ચાતો નથી હોતો. પણ મને એમ લાગ્યું કે આપણે એમેચ્યોર એસ્ટ્રોનોમર્સે આ વિષય વિશે પણ જાણવું જોઈએ. અને એટલા માટે ખાસ આપણે આજે એક પાર્ટિકલ ફિઝિસિસ્ટને આમંત્રણ આપ્યું છે. પાર્થો કોડા રીડર છે પીઆરએમાં. પીઆરએમાં હમણાં 3 વર્ષથી આવ્યા છે. એની પહેલાં એમણે બીજે પણ પોસ્ટ ડોક્ટરલ ફેલો તરીકે જુદા જુદા ફ્લોરિડામાં, જર્મનીમાં અને પછી ટીઆઈએફઆર એટલે કે ટાટા ઇન્સ્ટિટ્યૂટ ઓફ ફંડામેન્ટલ રિસર્ચમાં પણ કામ કરેલું છે. અને અલ્હાબાદથી બહુ જાણીતી સંસ્થા છે હરીશચંદ્ર ઇન્સ્ટિટ્યૂટ, ત્યાંથી એમણે પીએચડી કરેલું છે. અને એમનો જે સંશોધનનો એરિયા છે એ છે થિયોરેટિકલ હાઈ એનર્જી. અને આ બધું થોડુંક આપણે માટે નવા શબ્દો હોય છે. એમનો જે રિસર્ચ ઇન્ટરેસ્ટ છે એમાં ફિઝિક્સ બિયોન્ડ સ્ટાન્ડર્ડ મોડેલ, એટલે આ બધું જુદા જુદા મોડેલ છે આપણા વિશ્વ માટેના. એમાં એક સ્ટાન્ડર્ડ મોડેલ પણ છે. તો એના સિવાય બીજું શું હોઈ શકે? પછી લાર્જ હેડ્રોન કોલાઇડરમાં શું ખરેખર બને છે, ફિનોમેના શું છે, એની એમાં પણ એમને રસ છે. પછી એ કોલાઇડરમાંથી જે કંઈ માહિતી મળે છે, સિગ્નેચર, એમાંથી દળ કેવી રીતે શોધી શકાય? કારણ કે આ બહુ જ સૂક્ષ્મ થોડો હોય, દળ શોધવાનું પણ બહુ. પછી એવી જ રીતે ન્યુટ્રિનો નામના પણ બહુ જ નાના સૂક્ષ્મ પાર્ટિકલ્સ છે, એ કેવી રીતે કામ કરે છે, એમ ઘણા બધા છે. અને એમણે પબ્લિકેશન કેટલા છે એ નથી આપ્યું, પણ કોઈને રસ હોય કે એમના પબ્લિકેશન છે એના ઉપર છે, તો આમાં એમને એમની સાઇટના પેલા આકાર છે, જ્યારે રસ હોય એને આપી શકીશ. થોડુંક પ્લીઝ બેર વિથ અસ. એ બંગાળી છે, એટલે આપણા કરતાં થોડાક ઉચ્ચાર એમના જુદા છે. એમ દુઃખ વ્યક્ત કરતા હતા કે મને ગુજરાતી બોલતા નથી આવડતું. મેં કીધું વાંધો નહીં, અંગ્રેજી પણ મોટા ભાગના સમજી જાય છે. અને કંઈક ન સમજાયું હોય તો હું દુભાષાનું કામ કરીશ, પણ એ આપણે અંતે વાત કરીશું. જે ન સમજાયું હોય હું એમની પાસેથી સમજી લઈશ અને તમને ગુજરાતીમાં સમજાવીશ. એ દુભાષાનું કામ કરીશ. તો હવે હું ડૉક્ટર પાર્થોને આજનું લેક્ચર આપવા વિનંતી કરું છું. ડૉક્ટર પાર્થ.
I start with thanking organizers here and especially Dr. Nene and for inviting me and giving me opportunity to talk in front of you. And this is a wonderful moment for me because I see so many interested people. Even yesterday, all these lectures and in the evening, that sightseeing, all these interested people. It was a wonderful feeling for us. So today, Dr. Nene has described, I have two sorts of problems. One is that I am very weak even in Hindi. So I will speak slowly so that you try to understand. I make my transparency more pictorial so that you can try to understand from the picture. Also, any moment you try to understand anything, you can ask me question. You can stop me and ask me question. Second thing is that the idea I am trying to say is slightly different from yesterday's set of lectures or you exposed to. So it needs lots of mathematical skill, and here I won't use any mathematical equation. So basically I will try to prescribe them as simple form as I can in this lecture, and let's do it more interactive. Whenever you feel any question is necessary, just stop me and ask me question or ask me after the lecture. So I was thinking that as astronomer, so what you are interested in, all the yesterday's lecture or observing the sky, then you are basically interested what is happening in the sky. So in the star system or solar system, you are trying to see that what is phenomena occurring there. So especially you are interested in that. So you are looking at the sky and looking at some binary star or solar flares and whatever is happening now. But I don't know whether you know the fact that nothing is happening now. Actually, what you are looking at sky, everything happened in the past. So it may be few minutes, like something is happening in the sun and it comes few minutes to come at the earth. So you are looking few minutes back actually. And when you are looking at some star, some phenomena is occurring, then you are looking at the past actually. So in that sense, you are not looking at the sky for the present form, you are looking at the past. So the more distant object you are looking, further past you are looking at it. So it may be few minutes, it may be few million years ago, something happened and you are looking at that thing now. So this is one thing in observation, observation technology. But today I will talk about somewhat different thing, and we will mostly ask, we are interested in different kind of question altogether. So we will ask why we are today. Means what is the reason we exist today? What is the reason universe evolved such that it cooled down such a level so that life form could develop? So, or it can make some kind of solar system which has a quite big lifetime so that our life form evolved in that form so that human being come into the picture. So this is not obvious. So from the very beginning, this form took a long history and lots of change and branch happened in the course of flow, and it happened somehow. It is very surprising. So we are here. It is very surprising actually. So to come to this point, universe in this point so that it can sustain the life form. So we try to ask the question, what is the fundamental nature of this thing? So this question is asked in this two branch of science, which is one is cosmology and one is particle physics. They are interrelated. I will try to explain you why they are interrelated. And these two branches involve a huge scale difference. So as you see that I tried to draw their thing. The particle physics basically tried So particle physics basically try to understand very very small fundamental particle in nature. So what everything is made of. If you ask that question, you will mostly ask the molecules or different particles made of different molecules. But particle physics, that is actually encountered in chemistry or more low energy phenomena. But particle physics try to understand what is there, which is the more fundamental particles exist in nature. So more fundamental particles which can develop everything. So particle physics is try to describe that. I will basically give you the more pictorial view of that afterwards. On the other hand, this left hand side, this is a huge scale, 10 to the power 22 meter, and right hand side, particle physics describes as some scale 10 to the power minus 15 meter. So you see that scale we are talking about minus 15 meter to 10 to the power 22 meter. So this is the larger scale which is encountered by the cosmology, how our universe evolved. But fortunately, our universe, how they evolved, you may know this Big Bang cosmology and how they evolved. You have heard some of them. So they are not that much complex in nature. Like if we talk about, say, weather system of present Earth system, that is much more complex. Here, when universe evolved, there are some certain amount of fundamental particles were involved and they evolved. That description is not that much difficult. That's why we can try to explain those phenomena. So So I start with the standard model of particle physics and cosmology. So particle physics is going on for a few decades and it is a very successful branch of theory where they try to describe everything what you see in the universe is made of some fundamental particles. Fundamental particles means that it cannot break further. For example, molecule you see it can break. You see proton, neutron, electron, you know that. Electron you cannot break anymore. But proton, neutron you can break it further. And you will see that it is made of quartz or gluons. Some particles called quartz and gluons. So basically, particle physics try to understand how quartz, gluons interact. And what is the nature of their interaction so that they make protons, neutrons, and all this, everything in the world. So everything in the universe. So starting from a very fundamental small set of particles, you can explain everything. You don't need iron, nickel, hydrogen, oxygen, everything. You don't need anything. You start with a very fundamental set of particles. Like you learn that you start learning 0, 1, 2, 3, 4, 7, 8, 9, 10, 9. Then from that you can start any big number. 10 to what 20 you can write 1, 0, 0 you write. So basically you can write any number from this fundamental fixed of real numbers. Similarly, so particle physics try to do that. It tries to explain nature down to the scale of 10 to the power minus 18 meter, which is the scale of this quant I was telling. So, if you know, is our atoms are made of nucleus, something nucleus, and electrons are moving around it. And nature of that is not actually classical mechanics; they are described by quantum mechanics. And this nucleus is very small, and all over it, these electrons are moving. So nucleus is concentrated in a very small inner core, and this nucleus is made of this particle called quark. That length scale is 10 to the minus 8 meter. So particle physics is trying to explain the length of that scale. So this picture is telling when you are looking at matter, it is basically made of atom. Then atom is made of these nucleus and electrons surrounding it, and nucleus has this proton, neutron substructure, and that is made of some quarks. This is I try to explain that. And there are broadly three classes of particles are there in matter. One is called electron. You may have electron you must know, but you may have this muon, some particle called muon also. So those are the class of electron, muon, tau, and some neutrinos which has no electric charge. They also club as electrons. Other class of particles are quarks, but leptons interact. I will come to interaction afterwards. So quarks are the particles which is basically make this nucleus, proton neutrons, and they interact through strong interaction, something called strong interaction. So these quarks are there are several quarks. They have some quantum numbers also. And apart from lepton and quarks, there are other particles which is called gauge boson. So you know photon. Photon is another this gauge boson, one of these gauge boson. Apart from photon, this muon and W and C boson, those are gauge boson. So they are boson, and other particles are fermions. So gauge bosons basically interact between two particles. So if two particles are there, electron and electron are there, how they interact between them? Because this electron and some positron or electron, they actually exchange some kind of photon between them. So photon is a gauge boson that is exchanged between these two particles, and that's how they interact. It is like me and you is interacting through, I am talking, you are listening. So or when you talk, I will listen. So we are exchanging some thought. So similarly, gauge bosons are that kind of form, and that's how they are interact. And that interaction involves actually some particle attracting or repulsing, everything is happening in the nature. So they are fundamentally because of this exchange of gauge bosons. So I limit my lecture in this. Afterwards, maybe I will show pictorially these things what I told. So next go to this next part where this is the standard model of cosmology. So these are the standard model means for the last few decades people tried to discover that what is the fundamental nature of things happening. So particle physics side they tried to explain and try to do experiment. They tried to match between experiment and theory and came to that model we call standard model. Here in cosmology also, they ask different questions. They don't ask what are the fundamental particles. They ask that how universe will evolve such a level here. So they try to write down the biography of universe. Some kind of biography of universe they are writing. Try to write and self-consistent way so that they can explain every phenomena you observe. So that explanation needs basically Big Bang. So you may have heard that Big Bang cosmology. So this Big Bang is happening here. Now here, something huge explosion has happened. Some infinite energy explosion in a very small amount of space happened. Then, according to this standard model of cosmology, this small universe suddenly expands very fast, which is called inflation, and it expanded too fast, so that all the lumps and granularity those things are kind of smoothened out. So now the universe what we see is more kind of homogeneous and isotropic. So that is because of this sudden expansion of universe. So as of now, cosmologists try to understand universe after some fraction of second of after Big Bang. Then how universe evolved thereafter. So after Big Bang, this is inflation era is going on where the universe expanded very fast. And because of this expansion, universe, okay, so after inflation, it is like a soup. Particles are there and lots of energy are there. Energy and particles are kind of mixed up like a soup. And all fundamental particles are moving around with a great speed. So exactly here, this particle physics comes into play. So it no longer becomes a cosmology independent part. It becomes a kind of hand by hand you have to do with particle physics, and you need to know how they interact. That time these fundamental particles with a great energy, they are interacting each other. They are actually interacting with some forward wave, backward wave. Forward wave, backward means you know there are some interaction. AB interacting and producing CB. In chemistry also you know there are some mixture of two chemicals produce some other two chemicals. Similarly in particle physics also two particles interact to produce two other particles. In particle physics, so basically the interaction you have to explain that how they interact and how they evolve afterwards. So cosmologists try to explain that thing that how particles are evolving, and together what happens that is because of this huge expansion, universe also cooling down. It is no more that much hot. It is cooling down, and what happens that some of these particles they become kinematically or energetically slower down, and then some very interesting phenomena happening one step or after one step. Something like very heavy particles, they try to kind of decouple from the theory. Heavy particles, they kind of remain in the theory, they no more interact, they remain in the universe, stand still kind of thing. And other particles still interacting, and then if this temperature lowered, then electron and these quarks they combine, and these proton neutrons form, and gradually this nucleus is formed, and first hydrogen atom, which is the lightest atom, they are formed. And basically then this process has started from the lightest atom to heavier atom, they are gradually growing. So first this lightest atom and helium atom, those things are happening, and gradually cool down, and free electrons are no more there. That process happened, that free electrons no more there means they kind of couple with this nucleus. So they form that atoms. Then photons which interact with this electron, they are no more means interact that strongly with them. They can move freely. They form that some permanent background of photons. So you may have that CMB, cosmic microwave background. Those photons are resultant of this cosmic microwave background. These are the very strong evidence of this cosmological model, and eventually they tried to come up with this model. When universe is cooled down, all these nucleus they tried to come together, and they tried to make some kind of lumps, because of this quantum fluctuation they produce some fluctuation, and they eventually make some kind of cluster of particles, and that evolved to the present form where you get a cluster of galaxy, and eventually galaxy from system, solar system, star system, those things evolve. So they try to evolve, cosmology write down the biography of a universe
from the almost starting from the Big Bang, few seconds after Big Bang, to the present form of the universe, where all these galaxies, stars, planetary system we evolve and we come to the present form. And at present, if you look at the right side of this plot, this is very surprising thing. So this is something called pie chart. So that circle is a pie chart. So basically they try to see that total energy in the universe in the different forms. You know that Einstein's theory of relativity, then they talked about E equal to mc square. So basically energy and mass is equivalent. It is some same form in different form, same thing in different form. So so they try to calculate that how in different form this energy or mass is there. So in this left hand side, this in the pie chart, this circle, or you can have a stick still one. Okay, but I can show right now. I can show it with this one. So this is a pie chart. Okay. So this is the part which is called dark energy. Something like 74% or 3/4 of the universe is accounted for dark energy. So huge part of energy is dark energy. We don't know very clearly we don't know the origin of this dark energy. So this is the one part, and yes, 1/4 part is everything. Everything means, so if I tell you that what is universe is made of, then instantly you will tell the universe is made of stars, galaxy, all these matters around that. But that is not true. 3/4 is made of energy which is unknown, and that massive part of energy, that is mass part of energy, this is only 1/4 part of that total energy. That is this right hand side, this part. This part is 1/4 part is only mass, and there only these massive bodies are made of 0.03%. So what it will say that our galaxy star system, they actually makes only 0.03% of the universe. So there are huge parts unknown. That is very surprising. In this modern science, we are doing so precise measurement of everything, and suddenly we come up with this kind of models. This is something like we have seen in the experiment. This is not a model. So this is observed in the experiment, and through the measurement we see this 3/4 part of this universe is dark energy, and rest 1/4 is something called dark matter. We don't know what is the origin of dark matter also. And only very small fraction, 0.03% is our normal matter, what we see every day. And somewhat neutrinos is there, very small percent, 0.3%. Some 3 hydrogen telegrams are there. Thanks. Very good. So dark energy here. Oh, okay, now I got it. Yeah. Okay, thank you. So dark matter is here, and only things we know is here. These portions is we know, and we thought that the universe is made of that. No, universe made of mostly this, which we don't know. So this is the standard model of cosmology, and as you have already got some idea that cosmology and particle physics go hand by hand, and they try to explain each other's phenomena. So this dark matter and dark energy, also many particle physics are also involved to explain that what is the origin of them. I will try to come there, but before that I try to connect between this cosmology and particle physics. So this is called three frontier, energy frontier, intensity frontier and cosmic frontier. I don't try to explain everything, but I am trying to explain that there are overlaps between them. Some dark energy, cosmic particles, this dark matter is here, origin of the universe. So basically, these are the interface areas which are working very hard, trying to explain things. Now, I have two sorts of stories to tell. One is story of Higgs. You may have heard in the newspaper, some people may have heard more than that, what is Higgs and how Higgs, so many years we are looking for Higgs and how Higgs was discovered very recently. So, and a Nobel Prize was won for the discovery of Higgs. So this is story of Higgs. And other part I will talk. So these are two frontiers. Cosmologists and particle physicists were working. Some other parts are there, but I can explain this. Dark matter is on the other side, as I told, that which is the invisible side of the universe. In the universe, almost 80% of mass is invisible. That story is another thing which particle physicists and cosmologists are looking. So I can talk about that story also. So what you are interested, I will start that one first. So which one you are interested in? Story of Higgs or dark matter? Dark matter. No Higgs. Higgs. So I have to talk both. Okay, I start with say dark matter. Start with dark matter. So, as I told you that in the universe, this is so wonderful universe and everything is exactly what we need, everything is there in the universe. Water, source, mountain, river, plants, animals. So everything is made of, whatever we see is basically made of proton, neutron and electron. So almost everything you break down and fundamental things you will get in the not proton, neutrons are not fundamental, but basically you will see proton, neutron and electron. You won't see other particles I talked about, that muon or other quarks or other nebula. You don't naturally see them. Here in the air you will see the high energy experiment. But I will not talk about that right now. Basically, I want to say that what I already told, that you have a picture of this, how our matter universe is made of. Now, now I am telling something very fundamental. So you know this. If you have a wheel of a cycle and you are rotating the wheel of a circle, then you call spoke, means those are rotating with the wheel, and how they will rotate, each point of this spoke will, how they will rotate. So each point will rotate. So further point will rotate faster, but every point is rotate like that. So wheel is rotating. So after some time from here to here, so every point of wheel rotates at the same point. So if you plot that one, then you will see that so further point is going faster and lower point is going slower. So basically all points of wheel stay together and going like that. So that you can say, those I told that I want to use equation, but for few people who know that equation, I tell that velocity is proportional to radius itself. Velocity at each point, radius of itself. But on the other hand, if you know this law of gravity is something all gravitational objects, all massive objects, they interact each other. So you know that if you go further from a mass, for example, some sun is there, some other planets are there. So further you go, this force between them is slowed down. So you can write the velocity equation between these planets, force and this, what is the centrifugal force is there. From that you will get some equation. Why do you see this velocity or this distribution of velocity carries like that? So basically it falls down when you go outer, it falls down like that. It is not very visible, but it is like that. So basically that means closer to sun, some planet will go faster, and further from sun, they will go slower. That also you have seen that yesterday that some lectures on that how they are evolving. Now, so this is natural expectation we have that further you will go, it will fall down this velocity. That we have seen actually. So different planets, we try to measure its velocity with radius, and then it is like that. Venus, Earth, Mars, Jupiter, and this equation is governing here. Okay, fine. Then we go further. We told that okay, we measure the velocity of planets, and we are happy that what law of gravitation tells, it exactly goes like that. So we are happy with that. Then, so human being is like that, and they don't stop. They say, okay, we are happy with this one. Let's go further. In the galaxy, so you have seen Milky Way. Milky Way is our galaxy. So in the galaxy, we see different points, different stars from the center of the galaxy, and how they are rotating. Let's measure them. And so basically this is the galaxy, typical galaxy, and that measurement was done from Doppler sheet. Yesterday some discussion was there. So basically this is the center is galactic center, and then you are go further down. Sun is somewhere in between outer side, and some other solar system or I would say the star systems are there here, and you identify each of them, and you try to measure velocity from that kind of star, and from that Doppler sheet. That's what you did. Then you got very surprising here. Then you know this 1 by r, this potential, that law of gravitation is talking this one. And you know that this galactic system made of lots of dust particles. It is not like only one massive particle and all these planets are like that. There is a dust distribution. So you try to calculate what is the dust distribution, and from that you actually try to calculate this one will be the phenomena. It will be something like this one. So this is from everything you object all the matters in the universe, and from that you expect that curve, and this is that curve. And what you observe is something like very flat. It is unlike the previous one. Previous one, we expected this curve and we got this curve experimentally. But now we expected this curve and we observed something like flat with this thing, which is not imaginable. We cannot believe that this can happen. If law of gravity or law of interaction between two massive particles is true, then it cannot happen. This observation cannot be true. So then you try to ask different questions. Okay, we have observed. So then try to say, okay, by looking at the observation, what we can talk about the mass. So basically, velocity of Earth is you can calculate what is the mass of this particle from this mass of this particle and this. So if you see that your expectation is some velocity, but velocity is much higher, then you will recalculate, you know the mass of the Earth, and recalculate what is the mass of the Sun. Maybe we have done some mistake there. So that's how you recalculate. You recalculate what can be the mass within that system. So this observed level of velocity cannot be explained with this what we see in the mass. So you need something more extra. So huge amount of mass is extra, which is you don't see in the normal observation. So this is not the only experiment done. There are lots of experiments which is basically indicating that. So this is within galaxy, and this is some spiral galactic rotation part. That one also calculated, and that one also got with distance it is almost flat. Then these are the several experiments, and I don't want to go through each of these experiments, but very interesting one experiment is coming from this gravitational lens. I will try to explain that. So you have had this gravitational lensing term, this term. Okay, some of it. So basically, when light is coming and some lens is there, so you know that depending on that material and how this nature of this curve, this will go. This is concentrated at some point. This kind of things happen. So light varies because of this refraction. So similarly, it happens in gravity also. It happens in gravity due to general theory of relativity. What happens? The light is going. If some very massive particle is there, so this massive particle actually changes the. I would say that this is some term came in the general relativity. Space and time is no more independent. So space-time curvature, that massive body produce some kind of space-time curvature. So when some light is coming, because of this effect of space-time curvature, it will not go straight. It will straight. So you know some light is coming from. That point. One star light is coming here. You are observing here. So suddenly what happens? That you suddenly see that star not here. That means that light is coming not like that. It is coming that way, then coming here. But your point of sight become that. So you observe here. Similarly, because of this gravitational lens, you can see all over this one. So in between, some heavy object is there. Right? You pass through all around it. So you will see the same stuff here. So you will sometimes look at the odd kind of thing. So this is the odd kind of thing. So these are the odd kind of things. Here you see. This is the. So basically, this art is producing because of the some massive object is there in between, and if you see that massive object or don't see it, does not matter. But you can measure that mass, calculating how much curve was done. So curve because of the mass, depending on how much curve was done, you can calculate how much massive object is. Here are time. So how much time I have? It is 11 now. So this is called gravitational lensing. It is a very powerful tool for possibilities. And so something amazing thing was observed in the collision collision of two bullet clusters. So this cluster of galaxy, they collided. People observed it, and observed means not only observed in visible light, in the other infrared light and different light band also they have seen. They also tried to look through this gravitational lensing. What they observed, that this is some simulation, but basically the pictorial representation of this observation. Basically they have observed this galaxy of gas. So they are made of gas, they collided. So you understand this, when this bunch of this gas form of galaxy, they collided, they slow down. They collision and they kind of coil and they slow down and then they pass each other and then slowly they go. But what invisible part is this part, this bluish part. So it was seen that huge part of Mars already actually almost like non-interactive. They just like has not seen each other, passed like that, and they passed. Only visible part of gas, they interacted and they slowed down. They came behind that massive part of it. So this is the pictorial representation. This is the so-called dark matter, and this is the visible matter. Visible matter is like effect. So I have a simulation video. It can be interesting for you to just try to. So these are these clusters. They are coming close to each other. You see. So bluish spot is the dark matter part. They just non-interacting. They just pass each other. But visible part is this part, which is interacting in lag behind. This part just moved as if there is nothing happening with it. Then they try to rotate each other. So if you take care of this explanation of dark matter, then you have to come up with a theory that our universe, our galaxy. So we have shown that our galaxy is like that. Basically, then device picture taking account of dark matter is like that. So this dark matter, so we are basically immersed in the soup of dark matter. We don't notice them, but they are there, everywhere they are there. And that can only explain this way of phenomena, all these phenomena. So dark matter as a word, this is nothing new. I don't go all of them. So I am telling that from the very past, basically what happened that when we found out that each of these planetary systems, each of these planets, so you know that this planet, then what is the next planet, you did not know. But what you notice that there is something wrong with the velocity of this planet. That is because of the influence of the next planet. And then you see that some ambiguity, you have a theoretical expectation, but experimentally you see some difference from the effect of the next planet. So we don't call it dark matter, but people throughout the history, people basically told that okay, there must be another planet there which explains the velocity or fluctuations of this. And then after the advancement of our new telescope or something, then we found another galaxy. So that way we always proceed for the very past. So that we usually call that okay, it is fluctuating because of our its velocity is changing because of the next planet or next dark matter. So we don't call it dark matter. some dark planet. We don't see it, but something is there. So that's how we discovered planet after planet, and many things were done for the last century. So here problem is like that. We see something, but we cannot explain. So we call it dark matter. So what can be this dark matter? So now particle physicists come into the play. They try to say that this dark matter can be another fundamental particle. But our standard model, we know all of this standard model particle, how they interact. There is no dark matter particle. We cannot get dark matter particle out of this standard model. Only particle was neutrino, which could have been dark matter, explain dark matter, but neutrino is too fast, too energetic. It cannot be dark matter because it cannot explain all these phenomena. So this is not a possibility. So we have to come up with some other particle which can be dark matter. That's how people move to the standard model to beyond standard model. This is one of these things. So they call the standard model is incomplete. You need some other fundamental particles which can explain dark matter. So those are very weakly interactive particles. So they don't interact with each other that much. That's why they pass each other very slowly. Whereas that normal gas and visible particle, they interact. They have this electromagnetic interaction. But these dark matters have a very weak interaction. So this is one of these. So this is one of the most promising dark matter candidate we have as a particle. We call weakly interacting particles. So we don't know anything about what is their mass, how they couple, how they distribute in the universe. These are the many questions people are asking. I don't know that much, but I will come to the thing that if winds are there, heavy particles are there, we don't see because we don't interact. So we see some particle because that particle, that will share everything we see because that particle is interacting with us. How they are interacting? They interact through photons. So we see those particles. If some particles are there here which do not interact with photons, we cannot see that particle. Even though it is there, we won't see that particle. So it is like that particle. So it is very challenging to detect those particles. But there are several methods people are trying to detect that particle. One is direct detection. If that particle is there, sometimes, very rarely, but sometimes they interact with some detector particle, and then you try to see that how much energy is released. From that way, try to calculate that whether these intelligent particles are there. Similarly, some indirect detections are there. I don't go in that one. So another way is, you may have this large hadron collider where this proton is colliding at a huge energy, and so these proton collisions can produce some of this dark matter if we can see actually that dark matter you cannot see in the detector, but without seeing also you can get some significant signal from that, and from that you try to measure what is this properties of dark matter. So that's all I wanted to talk about dark matter and how people are expecting to detect them and how to explain that thing. But it is one open question. There are series of open questions, and you understand there are, and yesterday talk we understood that solar system, sun is so near around us, but so much surprise around it. Similarly, dark matter is another problem. It is everywhere. It is all around us, and it is making everything means it is telling that 80% of matter is made of that dark matter, but we don't see it, we don't detect it, we have no idea about it, what is that. So that is something amazing we feel everyday life in the science or experiment, this thing. So people are trying to come up with some theory, experiment, and that's how we progress. And we hope that eventually we will come up with a concrete idea about what is that. Okay, briefly I don't have much time, so I briefly try to say talk about story of heat. I already talked about what is the standard model of particle physics. So I don't go that much, but these are the fermions, and it has these electrons and quarks dipole, and these are the Higgs boson, and these are the scalar boson, which is Higgs boson. And we have fundamental particles of these many particles. This is the all fundamental mathematical symmetry. So this is kind of everyday symmetry is described by the mathematical area of physics, area which is called group theory. So particle physics is based on group theory, and another branch of physics which is called quantum field theory. Quantum theory, you may know that one branch of physics different from the classical mechanics or classical physics. Classical physics, everybody is deterministic. So you throw a ball, you know where it will go exactly. What is the momentum or velocity and what is the mass or position of that? You know exactly. But in quantum mechanics, it changes. This perception changes. It has a wave nature, and you talk about more probabilistic things rather than the exact nature of this momentum of energy particle. That happens when very small, you are talking about very small particle. You try to explain that, then you have to explain through quantum mechanics. You try to talk about electron, you have to describe by quantum mechanics. That is one thing. But particle physics deals not only small particles, but very energetic particles also. Its energy is too high. Its velocity is almost like light velocity. So quantum mechanics does not work. It needs something called, it mixes quantum mechanics with the special theory of relativity. So basically, it is relativistic quantum mechanics or quantum field theory. So this is one mathematical thing we need to calculate anything in particle physics. Okay, I am trying to just give you some essence of things. So symmetry and quantum field theory, these two are main basically two hands to do particle physics calculation. So quantum field theory is something amazing things can happen. For example, numbers may not be conserved. You know this energy and mass is equivalent. You can change one form or other. So similarly, what will happen that you throw very light particle, two electron positron of very light particle and collide, very energetic light particle and collide each other. What you expect in classical mechanics? They will collide and two marbles collide and they will go some other direction. But in quantum theory, what will happen? Two marbles are thrown with a very analogy is there. I don't quote me that I told marble thrown and that way, but I am just trying to give you an analogy. Two marbles are thrown with a huge energy and colliding, and it produces two elephants. So it can happen. It can change completely. It can produce two elephants like that, and not two. It can produce 10 elephants and something like that. It happens everyday life. In our everyday life, when we do a high energy physics experiment, we throw two electron positron, they produce two top quarks, which is very heavy compared to this electron. So hundreds of particles are produced and heavy particles are produced. So it can change the particle, it can change the mass of that particle, everything it can be changed. So that our perception about that particle, this classical physics will change. And this quantum theory correctly explains that those calculations, and we try to calculate that one, and we try to match with them in the experiment. In the experiment like Large Hadron Collider, we throw particles in very high energy and they bombard and they produce hundreds of different other particles. That's how sometimes you can produce this dark matter particles also. And then something called detector, which try to see. Detectors are nothing but a blocks of camera, digital camera, in some sense. In multi-layer digital camera. So basically, in each layer you try to see what is happening, what particles are produced, what is their energy, what is how their particle is moving. So basically, in different aspects you are looking at the detector, and from that you are trying to estimate what is the theory getting there, what is the fundamental theory producing that. Basically, that was something. And then something happened that this law of particle physics based on some symmetry, and this symmetry is telling that all particles, all fundamental particles has to be massless. So this is something amazing, that symmetry itself is telling that it cannot have mass. Then you are breaking that symmetry. You cannot write those terms which break that symmetry. So, but that theory is so long consistent. It's so long, so many discoveries was made consistently in particle physics. So we don't want to throw that theory. We try to change the theory slightly so that it can explain the mass. We know that electron has mass, muon has mass, this electron has mass. So, but we have to explain that, but within the framework of things. That's what is called Higgs mechanism. Higgs mechanism basically changed the perception. They told that something called vacuum energy state, and we are staying in the wrong vacuum. That changed the perception. So I don't want to go that wrongly, but so basically this explanation, Higgs, before Higgs there are so many people who worked about that. So this Higgs mechanism, what is explains the mass of the basic particles, work done by these lots of particles. Among them, these three people worked on Wilfrid here, and these are the people who actually took this Higgs model and some other theory of particle physics and combined together to make what I am now calling standard model of particle physics. This is another thing, that all particle mass are there. So some of these particles are very light and some of particle mass are very heavy. So orders of magnitudes are different there. And we actually produce all fundamental particles in experiment. In the different experiment, we actually produce electron, photon, muon, neutrinos, and different particles, different quarks also, tau, charm. These are the quarks. Everything was throughout the few decades we produce them, and we know their mass, their quantum number, how they interact with these things throughout the history. And most recently this one we discovered recently. So this is the large hadron collider I was talking about. This is at CERN, which is at the border of France and Switzerland border near Geneva. So this is the CP, this is the Alps range, Alps mountain range, and this is the tunnel. Yellow part is the tunnel underground. So in this tunnel, two proton beams, one in clockwise and another anti-clockwise, these two directions. These two proton beams are kind of moving very fast. You have to give them enough energy to move fast. They are moving almost near to light velocity, and by doing that, at some point they collide. So this is the LHC experiment. These 4 points where these proton beams collide, and they produce hundreds of billions of new particles. Okay, so basically some slide I was trying to say that LHC not only about particle physics, they have done many other things, like most famous is World Wide Web. You use www. That was invented here in the past experiment when you are doing some other experiment. And there are immense number of challenges, not only in the particle physics sector, in the solid state, in the superconductivity, many other branch of physics that is very challenging, because it is basically you are pushing your ability in the frontier. So huge amounts of efforts was needed for that. This is the schematic picture of the some detector. This collision happens here, proton. Then it produces billions of particles. They go through this detector. I talked about this snapshot of particles. So they keep this particle when they go through this detector. They produce some kind of snapshot in the detector. That's how we know whether some electron went, which energy went, whether some muon went, or some other electrons went. But we know the exact nature of this particle by looking at how they produce it at the detector. So this is a typical detector, one detector, where the figure of human being is like that. Typical human being is this small. It's a huge detector. And this is a typical collision experiment. When you collide one event, then this will happen. In the detector, they put a snapshot. These different colors are different particles, and these tracks, some particles produce some kind of track, some particles just try to rotate, and this circular track, and some particles don't put any track but deposit energy. So these kind of things happens in the detector. From that, you throw away all these unnecessary things and try to find what is the interesting part. That is the challenge. So this is our challenge, that how this data we collect is huge amount of data. So, but we have a limitation of how much data we can keep. That's why we throw away most of the data and keep it very interesting. We think it is interesting. Those kind of very small fraction of data we keep and to analyze. This is the computer system grid data. So grid computing. So basically they collect all the data and keep it there. Then they throw those data all over the world. Different grids are there. They exist all over the world. So it is basically now largest and highest energy particle collider. Is so extremely extreme. This is always pushing boundaries of existing technical and engineering solutions. So basically, by building this Large Hadron Collider, is new technology and other amount of science also involving. And at the end, what we are taking this data from this experiment, and we know what we have some theoretical calculations. We calculate in the theory, as I told, that group theory and the quantum field theory. In that sense, we calculate that thing, and we try to match them. And from that, we try to match what is our expectation on what we are looking at it, what we are getting at it. From that, this is the typical plot where we discovered actually Higgs. There are some other channels, but this is one channel where if Higgs was not there, we would have been got this line. But because of Higgs, we got a bump here. This bump is because of Higgs. So this is the announcement, CERN announcement of 4th July 2012, and these experimental groups announced that they have observed some Higgs-like particle. They are very careful. They don't call we have observed Higgs. They talk that some Higgs-like particle, which is scalar, properties are like Higgs, but we don't know whether it is actual standard model Higgs or not. So they told they observed some Higgs-like particle of mass 125 eV at 5 sigma level. 5 sigma level is basically how optimistic we are that we have seen some certain particle. We have seen the certain signal. So you know that when you see something, there are huge amount of background is there always. So how you confident that you have seen something not background, checking background, you are seeing something original signal. So this is some statistical quantity. People talk that we are say 99.9999% confident that we have seen something new particular, not something fluctuation of background. So basically in that term. So basically this is one signal, very
characteristic of Higgs particles. They Higgs decays to electron, positron, and beyond mu plus mu minus particles. And 2013, this Nobel Prize goes to these two guys. So this Gillard and Peter Higgs, and this is the event of that time. So basically, I tried to briefly say the Higgs thing, but basically both recent experiments, both in cosmology and particle physics, we are getting success, and we are very hopeful that we will try to understand many areas of particle and cosmology, and precise cosmology is also here. We can precisely measure many phenomena in cosmology. So interface area works are going on, and some answer we got, but there are many more questions are there. So I finish it here, thanking all of you for your interest and amazing involvement of this group. People are so much interested. They are from different professions, but they are trying to understand something which is not so easy, but they are trying hard to understand. They are looking, spending time, spending effort. So to make things. I congratulate all of you for that effort, and I really appreciate it. Thank you very much.
કોઈને કંઈ પ્રશ્નો હોય તો પૂછી શકે.
Sir, dark energy, how we can find dark energy?
Achha, dark energy is something more fundamental, means it is much more complicated than dark matter. It may relate with that vacuum energy. You know that even in the vacuum, actually it is manifested in quantum mechanics. Even in that vacuum, there are some energy in quantum. So it may be related with that. But there are many people are working on it, but it is not very easy because it involves some quantum phenomena added with gravity, which is not very easy to calculate at the present with our present understanding. So people are working, but it may be very simple solutions are there. It may be very difficult solutions are there, but we have very poor understanding still.
So the experimental age is not true.
Some experiments are going on, but those are different kind of, not like dark matter. So dark energy is completely different from what we call about dark matter. Dark matter is something real is there, but dark energy is something superficial, maybe because of this vacuum energy.
People have picked up the idea of modified coding mechanics to replace dark energy. What's your
Not dark energy, dark matter. So I tried to explain that expand observation basically pushed us to believe something called dark matter is there. So then first thing what you will do? So you looked at some phenomena. It is not matching with your theory, and you first think that okay, maybe Newton's gravity, what we calculate 1 by r potential, that was wrong in the last distance. After all, it matched correctly with our planetary system. Then when we go to in the galactic scale, it was completely wrong. So something may wrong at the large distance, it may wrong. It is the naturally people will think at first. For example, you know this special theory of relativity. It changed the Newton's law of gravity, Newton's law of motion. So basically, that was the special theory of relativity. Is a complete picture. In the low velocity regime, it changed their formulas so that it correct. When Newton's law of motion is correct, when velocity is, but when velocity is large, then this Einstein's law of relativity, special relativity is the correct picture.
So that is complete picture is that, and local picture which is true for our low energy thing is this one. Similarly, modified law of gravity. That was the first thing people thought about. First thing, okay, so change the law of gravity at a large distance. That initially people got success, but what happened, that lots of other experiment is doing, and not all of them are through just velocity measurement. Like that one I saw on this bullet cluster. Law of, that explanation with this MOND, modified law of gravity, they cannot explain that one. So that is completely ruled out. So we have to go to some other model. That is ruled out.
બીજા કોઈને કંઈ પૂછે છે?
How can we define that this is dark energy, not dark matter, and this is dark matter, not the dark energy?
Dark matter and dark energy. Okay. I have not talked much about the dark energy. So dark energy actually is different. Dark matter, have you understood that how dark matter, why we have to talk about dark matter? Dark energy is something completely different. I briefly tell you for you. So you know, in the large scale only gravity is how that people are interacting. All the masses are interacting. And how gravity will work? They will attract. There is no difference. So if universe made of all these particles, all the massive objects, they will attract. So they will come close together. They will stay together. They will be closer like that. On the other hand, what we see in the universe, it is actually expanding. And that's why it cooled down. And cooled down such a level so that this life form has produced. So there is something which is pushing against gravity, and which is much more powerful than black hole. That is dark energy. So dark energy, origin and expansion, everything is different. But we don't have very clear understanding what is dark energy. It is related to something I should not tell you. It's state energy or something like that. So afterwards you will get. But basic idea is that it is pushing everything apart.
અમે નહીં. બીજા કોઈને?
According to the most accepted theory, Big Bang. So my question is the material, the primary material of the particle for the Big Bang, from where it came from.
Okay, so Big Bang started with a singularity. It is called singularity. So we have, as a physicist, we have no idea about what is Big Bang and how it happened. We don't know any history before that. So basically, that singularity, or when it happens, it erased everything before that. So we won't know anything about before Big Bang. We only talk about, as a science, we can only talk about something after Big Bang. But some explosion happened, and huge amount of energy explosion with a very limited space time, that happened. Then it started expanding. We, as a cosmologist, they try to explain thereafter. They cannot talk about before that. We have a limitation. Physics has a limitation at that singular point. Singularity we cannot explain. We have no explanation.
So do you support any supernatural thing for that?
People can have their understanding, different ways we can, but as a scientist, we have no understanding, we don't know anything about before that. No experiment, nothing will show up or manifest anything before that, because that is a singularity. Everything breaks down.
Anybody else? કોઈને કંઈ પૂછવાનું ન હોય તો let us thank the speaker. અને હવે હું અમારા મેનેજિંગ સમિતિના સભ્ય એવા પ્રોફેસર મિહિર જોશીને બોલાવીશ. એ આપણા સૌ વતી ડોક્ટર પાર્થોને મેમેન્ટો આપશે. મીરભાઈ જોશી, સૌરાષ્ટ્ર યુનિવર્સિટીના ફિઝિક્સ ડિપાર્ટમેન્ટના પ્રોફેસર અને ગુજરાતી ટીવી પર transfer once again